All right. Welcome everyone to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk. But if you have questions, you can unmute and ask questions or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audience. So no classified discussion is allowed here. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me briefly introduce our speaker today. It is an honor to host Dr. Boris Kramer, who is an assistant professor in mechanical and aerospace engineering at UC San Diego. Prior to joining UC San Diego, he spent 4 years as a postdoctoral associate in the Department of Aeronautics and Astronautics and Aerospace Computational Design Lab at MIT. He received his master's degree and PhD in mathematics from Virginia Tech. Prior to that, he studied mathematics in technology and mechanical engineering at the University of how do you pronounce it?
Karlsruhe in Germany, yeah.
Karlsruhe in Germany. Thank you, Boris. And he is a member of the SIAM and a senior member of AIAA, where he also served on the multidisciplinary design optimization and is active in non-deterministic approach technical committees. He is an 2022 NSF Korea awardee and won a Department of Defense Newton Award in 2020. His research is funded by the Office of Naval Research, the Defense Advanced Research Project Agency, and the National Science Foundation. His research interests are to develop computational methods and numerical analysis for control, optimization, design, and uncertainty quantifications of complex and large-scale systems. All right, today Boris will talk about structure-preserving learning of high-dimensional Lagrangian and Hamiltonian systems. Please enjoy and expect a wonderful talk. Now let me ask a couple of questions so that in order to make this seminar somewhat informal. Okay, first question for you, Boris. Obviously, you are very passionate about, computational methods and numerical analysis for control optimization. And also, I know you are really into reduced order models. Is there any moment in your life when you realize, wow, this is it. This is the field I would like to commit my career. Do you have that moment? And if you have, would you share that moment with us?
Maybe to understand the question, was there a moment where I said, I found my career, I'm happy, and I'll stay doing it?
Yes.
Okay. Yeah, I kind of did that when I was, I think maybe an early master student, starting my PhD. I did an internship somewhere in industry, and it really wasn't thrilling me. And I felt like there's so many things to keep answering and to do research on that I wanted to kind of go in this direction. And that high fidelity models are everywhere, but they're not always super practical. So reduced order modeling is it.
Awesome. All right. Well, second question for you.
Mhm.
As we all heard the introduction about you, like you've been getting a lot of awards and fundings from various sources. In that sense, you've been quite successful as an assistant professor as your early career already. That's a wonderful job. Any secret, any hint for future faculty,
Mhm.
person, people?
Yeah, it's a very, very good question. I thought you were going to ask me if the 49ers win the Super Bowl, but no, I think a lot of us is keep talking to people, listen to the big trends that are happening. There's so many great areas to work in at the moment. It's equally important to work on a great problem as it is to work on a good solution. And I think combining both has worked well, but I think it's a good starting point.
Good application and good
Good
method.
application and good
Yeah.
methods, yeah.
Good tip and good hint. Okay, the floor is yours, Boris.
Absolutely. Thank you so much, Jungso, for inviting me here to give this remote seminar. And for all the attendees who I don't see, I don't have the tiles up here. So if you're here and, I hope it's not, some of it is to your interest. Um, my collaborators on this work are diverse. So we have from different departments. We have the main driver of all of this work is my postdoc, Dr. Harsh Sharma. He's been involved in all the papers you'll see today in the methodological development, and then also started collaborating a lot more outside of our department with these two gentlemen, Iman, who's a graduate student here, and Mike Tully. They're both roboticists with David Najera and Michael Todd. They're from structural engineering. They have some interesting applications that they want to use our methods on. And then Zhu Wang is a collaborator of ours on the methodological side at the University of South Carolina. This work's been funded by DoD Newton, so by the Department of Defense, by the National Science Foundation, by the Korean Institute for the Advancement of Technology, and by the Office of Naval Research. To get us started, I think we all know in this seminar that data is becoming more and more accessible. We can produce more data, we can store more data, and the question is, as engineers and physicists, how can we harness this data and learn valuable things from it while not throwing everything that we've developed over the last 100 years away? Data is often high dimensional, but high dimensional complex systems often take very long to run. So the goal here is, if we do have systems of the kind that I have here, a dynamical system that evolves in a nonlinear way and might have complex inputs, inputs acting on a certain way on the flow of the system, then what can we do to learn such systems from data? We can obviously do machine learning. I'm interested in a few other methods to get us really into the predictive regime of these things. In general, large is a topic of discussion that we could discuss for an hour now. What is large? But if n is reasonably large here, in my case, over 1,000, then most learning methods will not be able to learn in a 1,000-dimensional space. There will be some sort of a reduction needed in all of these methods. My point is, and many of us would probably agree in this seminar, for physical systems, we have to incorporate knowledge that we know. So let's build on what we know and let's really combine the best of both worlds. Now, I want to talk specifically about structured systems, systems that have something more than just something mathematical that we know about them. That's just, we don't just know that they're having a quadratic or a cubic term, but we might know that it preserves certain things. For example, there could be conservation laws that are underlying most of physical systems of their derivation, symplecticity, reversibility, interesting configuration spaces. I'm showing you a few on top here. Plasma, if it's engineered, or solar plasma has these properties. I'm showing you later something about soft robotic fish, mechanical systems, second order systems. And really there's a long history in modeling these things to incorporate a geometric structure, to discretize them correctly in space and in time, and therefore to get predictive simulations for such problems. Only caveat is that these predictive simulations can be quite expensive. What happens, the time integrators are generally quite expensive. They might be implicit, and the system dimension is large to cover complexity. And so what I'm interested in, and what we'll be talking about it here, is there's a need for physics preserving, not just informed, but physics preserving reduced order modeling. So something that brings down a dimension, but also preserves the physics. I'll structure this in two parts. The first part we'll talk about Hamiltonians, and the second part we'll talk about Lagrangians. I'll hope to spend more time on the second part. And two citations are here. I'll also have them up later again if you're interested in this. So I'll start a little bit more general with gradient systems. Actually, this is a typo here. Should be a general infinite dimensional gradient system where I have a field y that I'm interested in. X is my spatial variable, t is a time, and basically the dynamics as it evolves in time is governed by a linear differential operator and then a variational derivative of this functional h. And here in my talk specifically, I'm breaking up h into things that have quadratic nature and things that have higher order polynomial or non-polynomial nature. Now, if this L has a specific structure, for example, if it's skew adjoint, then we often refer to this system as a Hamiltonian system. The Hamiltonian will remain constant, and we call the partial differential equation conservative. If L happens to be negative semi-definite or negative definite, then we can refer to H as an energy function or as a Lyapunov function, and we could have either respectively a non-increasing behavior or a monotonically decreasing behavior, and we would call the PDE dissipative. In structure preserving space discretization, then you take this PD and you move to an ODE, and you would give an ODE that looks as follows, where basically this gradient of this H Hamiltonian or Lyapunov function appears, and where D has a very specific structure. Now, this is all in very high dimensions, and we're trying to reduce the dimensionality. So given some trajectory data y at certain time steps, I would like to learn the evolution of the system. So I'd like to get a dynamical systems representation that works in lower dimensions. So it's faster to execute. To go back to the gradient systems for a second, there's special cases, obviously. So when D is skew symmetric, skew adjoint, anti-symmetric, any of the three words you might be familiar with, which really means D is minus D transpose. Then we call this a Hamiltonian, and what we can show is that for any times such that T1 is less than T2, the Hamiltonian is conserved. So the Hamiltonian evaluated at the flow y of T1 minus the Hamiltonian evaluated at the solution at time T1, so T2 minus T1. If you work out the integral, well, the skew symmetry is exactly what gives you the zero here. So you have conservation, and this is what we want to track in numerical solution. If D happens to be negative semi-definite or negative definite, then you have a gradient flow system, and you have a dissipation. So the Hamiltonian a solution of time T1 minus, or the energy at T1 minus the energy at, T2 minus T1 would be less than zero. So the system dissipates energy. In numerical schemes, if you want to do just PD discretization, they would respect this, and we want to respect these properties in reduced order data-driven modeling. So let's focus on this talk on canonical Hamiltonian systems, just for the purpose of the first 10 slides. In canonical systems, I can separate the state into two distinct physically interpretable quantities, the momentum and the generalized momentum. The matrix that's in front of the gradient of the Hamiltonian is the simple canonical Hamiltonian structure. It looks like the identity minus the identity on the off-diagonal. And lastly, there's a symmetry that we can often use in the full order model operators that arises from space discretization. If you're interested in other gradient systems, then you should look at this. If you're interested in specifically non-canonical Hamiltonian system, then Anthony Gruber and Irina, who I think is on this call, have done some work in this area to do learning of these systems. So canonical case, what we would like to do, I would basically like to learn a system of the top part that looks like Q dot P dot is equal to that, but I'd like to reduce the dimensionality first. I don't want to learn in a 1,000 dimension. So to do that, I assume I have data. I store snapshots of full order simulations in the matrix Q and P just to separate these physical quantities. I have assumed here in this talk, and we'll relax assumptions as we got further into the talk. In this first part, I'm assuming that I know something about the nonlinearity in the functional. So I know something at the PDE level. I do not have to know this at the code level, but I have to know it at the PDE level. If I know this, then I can evaluate non-quadratic terms on my state. So I can build these forcing matrices, both for a momentum and a generalized momentum. And I can also build time derivatives with a finite, for example, finite differencing scheme. If I have noisy data, then maybe I have to do something else, total variation differentiation or something else. But what I do here is I store data, I evaluate something that I know at the PDE level, and I compute time derivatives. Now I have to reduce my dimensionality because n could still be in the thousands or 10,000s or 100,000s. To do this, here we have to be a little bit more careful. So we want to use proper symplectic decomposition that was, proposed in this paper by Peng and Mohseni in 2016. So basically, you want to make sure that the projection is onto the right space so that this projected dynamics can still be evolving in a symplectic flow. So here, the way to do this is you basically compute this phi matrix. You set that these two projection matrix equal to this phi matrix, and you get this from this cotangent lift algorithm. Now you project your states linearly. Again, this is not autoencoders, nothing else here. You can project your states linearly, you project the time derivatives linearly, and you project the forcing linearly. We have done other work where we looked at manifold expansions here, but for now in this talk, we'll just focus on linear projections. So now I have projected data, and I need to figure out what do I do with this projected data. So I know now that this data lives in a low-dimensional subspace. I've established that. Now in that low-dimensional subspace, I impose a Hamiltonian. So if I were to write things down on paper, I would arrive at the case that my Hamiltonian, the low-dimensional subspace, would look like this. It would have, Q transpose dq q hat. There would be an equal part with the p variables, and there would be my nonlinear terms. Now I would also know from this expression, these are scalars. The Hamiltonian is a scalar function, that dq and dp has to be symmetric. And that's the knowledge I have to embed in my optimization. I would not see this if I go directly to the governing equations. So here in the Hamiltonian, this becomes evident, and so therefore we carry this through. My state dynamics are now given as follows. Okay, so now I have dynamics, I have a Hamiltonian, and now I would like to base this off of basically this operator inference framework that Benjamin Peersdorfer and Cameron Wilcox worked on in 2016, which is a really great and flexible framework to efficiently learn low-dimensional models. So now what we do here, since in this part of the talk I made the assumption that I know what at the PDE level what non-polynomial terms I have, I put everything I know on the left-hand side. I put things that I don't know on the right-hand side, which are these operators. I constrain my optimization by symmetry conditions, and all I have to do is solve for these two. These least squares problems actually separate. So I can separate them as follows for a problem in P and in Q. And the solution to this problem is actually given by a Lyapunov equation. So you can either minimize this with a solution of your choice, or you can solve a Lyapunov equation. We found that solving these Lyapunov equations with specific symmetry conditions is kind of a nice way of doing this. Okay, so now we have a few operators, and what we basically have now is a reduced order model. We have learned these operators had, and we have a reduced order model that evolves the reduced states with these symmetric matrices in linear terms. We study this for a little bit in terms of what can we say. So if you had done reduced order modeling, which is projection based often, if you had done this in a Galerkin projection framework, so if you take your PDE, you discretize it in space, you multiply, you have reduced spaces that you want to project it on. So if you had done this, would the learned model from the least squares problem be close to the projected model if you had done everything intrusively? And while it's not a result that has a pre-asymptotic error bound, at least it tells us that the operators that you get from projection, which we call tilde operators, are close to the operators that we get from learning by epsilon. And the epsilon kind of, so for every epsilon, you can find an R that satisfies this. The unsatisfactory thing about this result is that we don't quite know how epsilon depends on R. But anyway, so asymptotically, we have this result here that at least we learn the right operators. Very recently, we also looked a little bit at the error that implies now on the solution. So if you were to solve your full order system from 0 to t, and you solve your reduced system from 0 to t, and you inject this reduced state back into the full state with your matrix phi, then you can bound this error by using some Cronwell inequalities as follows. There's a constant that I'm not going to go into details in, but basically the error has three components. There's a projection error that you have in all linear methods. So the error in the projection of your state. You have, so to speak, a data error that tells you, well, how accurate is your time derivative scheme that you have approximated. And then this is really the error we focus on more, which is the optimization error that tells you, well, how well are you learning structural properties of this DR matrix that you have? And this is something that we study a little bit more in this paper. I'm not going to go much into it, but I wanted to tell you there's two types of ways that we can bound the errors. And there's some Lipschitz constants involved that I don't have defined on this slide. So just wanted to bring this up. So now I want to show you some results here, going right into what can this Hamiltonian operator inference do. Let's assume I have a cubic system, cubic Schrödinger equation, which has the following time continuous Hamiltonian. So the Hamiltonian can be broken up as we had it before into a quadratic component, and here we have a quartic component. This nevertheless does lead to a canonical Hamiltonian PDE, where we have this canonical matrix of 1 and -1. We have spatial derivatives. Those are the things where you typically need to understand what spatial scheme has been used to discretize the PDE into the ODE. And then we have simple multiplication of states, like q squared times q cubed and p squared times q. Those are multiplications you can perform element-wise on any discretized vector. Okay, so that's what I mean. These are kind of spatially local terms, and these are terms that need spatially neighboring information to compute derivatives. There's invariants of motion that are known for this system, so we'll study those. The mass, for example, is conserved and the momentum is conserved, and they're defined as follows. So you'll see some plots later that look at these invariants of motion. We mainly conserve the Hamiltonian structure, but they kind of will see that at least the mass is perfectly conserved and the momentum is very well conserved. So for a reasonably low state dimension here, so 128, we look at the state error, so the relative state error in training and in testing. So in the testing regime, I think I didn't say what kind of times I'm looking at. It'll become clear in the next plot. But I'm doing a reduction to even number of modes between 2 and 12, and I compare my learning method with an intrusive method, intrusive proper symplectic decomposition by Peng and Masseni. So if I had known everything and I didn't have to learn it and I have full access to my system, this is the error I would get. And if I learn it, I'm pretty well until about 10, and then my error flattens off. In testing, we do pretty well, comparable to the intrusive method, which is quite well, but keep in mind, the axes are different. The testing error, of course, is larger than the training error here. Okay. We'll look at the invariance now, or the Hamiltonian first. So we look at how does the Hamiltonian at the full order model level evolve. So H at Vy hat. So how does it evolve and how is it conserved? So if we look at the full order model energy, it's bounded by about 10 to the -5, and it evolves in the cyclic nature. That black line is the end of our training. So we train for 20 seconds and we test for 100 seconds. It's important to notice that since we maintain the structure, even if we go into the predictive regime, that structure is maintained. The model remains stable, the model remains predictive and keeps its predictive capability. So that's important. Not all methods, unstructured methods that don't embed physics are typically not seeing that. If we model the reduced order model Hamiltonian, it's a little bit of a different way of looking this. We also conserve this for dimensions here, but really I think the full order model is the right way to look at it. Was there a question? I heard a noise. Someone have a question?
I think it was noise.
Okay, good. Now we look at invariance. We look at mass conservation and momentum conservation. So again, we look at them at the high dimensional level, at the full order model level. The momentum on the right side is perfectly conserved, down to machine precision. And the mass is conserved up to with an upper bound of like 10 to the minus 6 for our operator inference model, and the intrusive model actually conserves it perfectly. We did not bake in any constraints to enforce that, but that's kind of a byproduct of learning the Hamiltonian structure and the symplecticity, right? Okay, so this wraps up my short part about the first 20 minutes about Hamiltonians, and I'd like to spend the next 25 to 30 minutes focusing on Lagrangians.
Oh,
And I'll take combined questions at the end if that's okay, just to make sure we'll get through most of the stuff. So now we focus on Lagrangian models. They have structures as well. And again, this methodologically, this is based on the work that Harsh has done, and then we'll see several extensions and actually nice applications. So why is Lagrangian structure now important? Why is that something we should focus on? Well, classical methods here, or a classical example is you have a beam which transfers vibrations. It's vibrating, it's supported at both ends, and you might excite it, and you start measuring the vibrations of this. Here it's modeled by an Euler-Bernoulli beam model. And now you could say, well, I mean, it's a mechanical system, it's second order, so I could learn a second order system. So I could do, for example, this method called operator inference. I could just write x double dot as something on the right hand side, and I'll just learn it. If you do that, in training, everything would look perfect to you because you're having a relative state error plotted against the reduced dimension. So you're testing different reduced models up to order 20, let's say. And you see as you increase the dimension, your model error your state error goes down. Your reduced model in the training data produces the result that your full order model does. Okay, so now you say, well, what is that any good? I want to make predictions. And you wouldn't see the error in the prediction until a much longer time. So I think here we trained for like 0.05 seconds or 0.1 seconds. So the black line is again indicating how long we trained. So we let this vibrate for a little bit. And then we make predictions. So you train and everything looks good here. And for a while, actually, everything looks good. It looks like your energy error is bounded by, I don't know, 10 to the minus 5, 10 to the minus 4. And then at some point at 0.8 seconds, that energy keeps growing, which means you just ran into this is a byproduct of you not conserving the Lagrangian property correctly here. The energy keeps growing, solutions blow up in finite time. And despite you learning a second order system, you have basically no predictive accuracy at some point. Okay. So we need to do something. Let's look at the mechanics of this problem. So here we write down what Lagrangian dynamics are. We need a finite dimension. We're in finite dimensions now. We need a configuration manifold Q. We need a state space TQ and a Lagrangian L, which again measures is a scalar quantity. If we allow forcing, the Euler-Lagrange equations are derived from this Lagrangian and external forcings as follows. We take the partial of the Lagrangian with respect to Q, take the partial of the Lagrangian with respect to Q dot, and we have a d over dt here, and then forcing could act on the right-hand side. So if we now go to, this is the general form, if we focus on simple mechanical systems, there's a certain way that the Lagrangian splits and that the kinetic and the potential energy separate, and their dependence on Q and Q dot. So simple mechanical systems, the kinetic energy is quadratic in this Q dot, and the potential energy is quadratic in Q. We also know that again, by these being scalars, that there would be symmetries involved, and we know something about positive definiteness too. Forcing, on this slide, I'm telling you that forcing I model with simple dissipative linear forcing, and I allow a linear time-dependent input here as well that acts on the system. If I do this, I arrive at a simple linear second-order system, but I know about this system that K has a symmetry, that M has a symmetry, C actually might also have a symmetry depending on how I choose it, and then I know that there's a linear forcing acting. Okay, so that's one way to do this. I can expand and also use this Euler-Lagrange principle to look at nonlinear wave equations. So now I'm going a slightly one level up, so I'll go to the PDE. So what if I have a wave type equation? So second order in time, one-dimensional in space, where I have some nonlinear terms. Sine-Gordon equations being one of an example here. So I have some nonlinear terms here that act on the potential energy. So UNL is really this nonlinear term in the potential energy. Okay. So if I were to discretize this in space with a structure preserving, for example, a symmetric finite difference or pseudospectral methods, then my space discretized Lagrangian would basically look at the Q variables with respect to T. It would discretize my spatial derivative with a certain discretization scheme. So this is this matrix T here, and I would have my nonlinear potential energy being subtracted here. This would all lead me, this is where I want to end up, to a system that looks like Q double dot is KQ. K has symmetry, again, this is important. And nonlinear parts, if I know that nonlinear potential energy, then I would get this contribution by taking that derivative. We know that this full order model conserves the total energy, which is defined as follows. Okay. So this is a principle that we also want to, quantities and qualities that we learn from this, we want to use and learn in the model learning. So usually when you start reviewing, you're never having all of the work. There's a large body of work in the machine learning community that has focused on Lagrangian systems, for example. How can you learn them from images? How can you learn them if you take pictures of robots? I'm focusing here on the model reduction aspects and what has been done there. Seminally intrusive projection-based methods for Lagrangian systems came out by Jerry Marston in 2004. And Kevin Kahlberg and a group at Sandia picked this up in 2015 and did some really nice reduced order modeling for nonlinear Lagrangian systems. This was intrusively, so we want to look at non-intrusive things. Miles Cranmer has done excellent work there, and I believe he was a speaker in the seminar series too. He did some nice neural network work and then extract by incorporating Lagrangian systems and a couple of other people. And this list could, in 2023, keep growing and growing. We noticed that many of these look at very low dimensional systems, so we want to go to something in the hundreds, thousands, tens of thousands. Operator inference is kind of where I feel is quite flexible in learning these things. So, but it doesn't allow for it wasn't written with constraints to start with. So really incorporating the Lagrangian constraints, just as we had done in the Hamiltonian case, is what we'll be doing in this work. There's also work that came out pretty much simultaneously with our work on operator inference for linear mechanical systems. This was by Peter Benner's group and Pavan Goyal, who I believe was also a speaker in the seminar series. So we will embed Lagrangian structure into this operator inference framework now. And everything here will look very similar to what I've done before. Again, now I only have in the Lagrangian, I just have basically one state. I don't have to separate my states in the P's and Q's anymore. I have a second order system. So I'm collecting state data, I might collect output data, I might collect input data, depending on if I have inputs or if the output is different from the state. Now I don't have to do proper symplectic decompositions. I'm good with just a single value decomposition. I project my data. Now I'm in the space where I can learn things. This is a manageable dimension R, it could be 10, 20, 30. And in this dimension, I still need derivatives. I need a first derivative and I need a second derivative, and I would compute them with some time stepping scheme. Okay. Same thing as we did before. I would now look at, well, what is it that I need to conserve, or how would the dynamics of the Lagrangian evolve in this space? So I'll write down my Lagrangian principle, my Lagrangian function, very simple here as quadratic. We'll change this to be nonlinear later. And I allow myself again a reduced forcing that looks as follows. And then I would again recover a Lagrangian system that's second order, that has certain properties, for example, the symmetric K that allows for forcing and has an output. And now we're moving pretty much like before. We set up a constraint optimization problem where we have constraints on K and C to be symmetric positive definite. And things that we have pre-computed and obtained from the data are Q, double dot, Q dot, Q, and U. We know what inputs we have. And then Lastly, we could learn the output matrix E hat if we wanted to. We solve these things with a constraint with the CVX toolbox. So we minimize this problem under constraints. If you want to push it to nonlinear wave equation, so if you want to add some nonlinearity here, then at this point, again, we'll relax this at the next level. We would have to know this component of potential energy at the PD level. If we do this, then we can evaluate our that nonlinearity at the state. We make the same projection, and we solve our optimization problem again. We'll see some results for this later. Importantly, I think really the symmetry and positive definiteness is what gives us a long-term predictive accuracy. If I do this with a sine coordinate equation, which is a prototypical test problem for this, which has this nonlinear wave structure and a non-polynomial term on the right-hand side, I'm comparing again intrusive with non-intrusive. So the method we're looking at is Lagrangian operator inference. In training, which is 5 seconds, is good. In testing, which is 5 times longer than the training interval, we're also doing very comparable for low order models that go up to R is equal to 15. Again, axes are different. Keep an eye. Left is a state error for training. Obviously, that is much lower than the state error for prediction. Okay. We want to look at energy errors. So we see that we have a bounded energy error. If we do this intrusively, the bound is somewhere in like 10 to the minus 2. If we do it non-intrusively with Lagrangian operator inference, we see some cyclic behavior, and we would have a larger bound. But again, for long-term predictions here, I'm showing you even more. So this was trained for 5 seconds and tested for 25 seconds. Here we're looking at 5 seconds, and I'm showing you that for 105 or 110 seconds, we can make stable predictions. And I could run this for 300 seconds if I wanted to. That's really what the structure gets you. Let's look at solutions. There's certain wave type structures, solitons that build up. How do we capture them? So the full order model at 5 seconds, that's the end of training. At 15 seconds and at 25 seconds, that's 5 times past the training interval. We're doing pretty well here. The green dots are basically showing what the curve would look like after this, and we capture basically this wave pretty well. Okay. So then we wanted to say, okay, so this is a wave equation. Let's go back to a mechanical system. The motivating problem here was to look at the soft robotic fish. We found this in this. This is the group of Daniela Roos at MIT is doing a lot of work on soft robotics, and so basically this is explained nicely in this paper. So you have these little fish, and you want to actuate them, and really the actuation happens along the center line of this fish. This is the important part. And so those are swimming around. You see a few snapshots at some milliseconds taken from these simulations there. Obviously, these are soft fish made from a silicon type material, so you really have you have a continuum model here that you have to deal with. There's a nice cat model that was developed by the group of Thomas Moyer. You can find more about this paper from 5 years ago. And basically, this just shows the actuation mechanism. So you see that tail here. The point of interest is kind of like the motion of this end point at the center line. You have a certain center line beam that is a reinforcement. You have a silicon hull, and then you actuate your chambers sometimes by pressure, sometimes by the pressure of a fluid pumping in. Okay, so now we look at the quantity of interest, which is this one-dimensional quantity at the end. So here I have like a sigmoid input. I look at I excite the fish with a sigmoid. By the way, the full order model dimension is 780,000, so this is quite large. We have this displacement, and we show it for the high dimensional problem, and we show it for a reduced order model of dimension 2. That's pretty good. Other people have also worked, a group of Peter Benner, Stefan Werner has worked on this with different reduced order models. This is a nicely reducible problem. Relative errors are low, and the energy, most importantly, here we train for 1 second, extrapolated 2. You see the energy doesn't change anymore because we have a nicely predictive model. Now we use a step input. So this is a control in. So we trained it with a sigmoid. Now we tested with a step. They have very different characteristics and frequencies that they excite. So even for different inputs, this works pretty well. We now see the step response of the full order model and of the two different reduced order models, intrusive and non-intrusive. The displacement errors are probably better here to see than to compare all these circles and dots. And lastly, the FOM energy in both cases remains very nice and stable. So no energy growth or anything. Okay, so that was our benchmark problem. And by the way, you can download. This is really nice. Peter Bennett's group has the more wiki up, so you can download this model if you want to and play around with whatever method you have. Okay, so this was a benchmark model. So and then some of our colleagues here in the robotics group at UCSD got interested in this, and so now I'm just showing you 5 slides or so about actually building something like this here at UCSD. So here I have some videos. I hope they're playing. Jungso assured me they would be playing. On the left side, I'm showing you a video of a trout that's swimming. So this is an actual experiment where you have a water tank, you have a stream. So you kind of, why do fish swim up the stream? And you have this trout swimming. So let me go. Oh, no, it doesn't. Let me see. I'll show it again. So focus on the left video. Can someone tell me what's the catch of this left video? If someone has seen it, you will know it. If you haven't seen it, you won't know it. Or maybe make a guess.
The fish isn't alive.
The fish is not alive. Yeah, the fish is dead. Which really is interesting. They put a dead trout in there, and just the body motion and the way these fish can move allows them to swim with very low energy, like zero energy upstream. And so that's pretty impressive. Obviously, we would like to replicate this in engineering. So on the right side, you see a video that actually is from our collaborators here at UCSD, one building over. They built this soft robot. They actuated with these kind of like pneumatic chambers where they put in pressures. So these are the control signals that you have. So you have 1, 2, 3, 4, 5, 6 control signals, I believe. Yeah, 6 controls that you can actuate. And you see this thing on the right-hand side is basically moving. Okay, so that's good. So they want to actuate this thing. This is a soft robot, so it's a continuum model. There's a discretization software that's a little tricky to use, but we've used the 250,000 dimensions. The nice thing is this is typically segmented, so they produce individual segments and kind of patch them together. It's 6 controls, which are these fluid elastomer actuators. They kind of also change the actuators all the time to get better performance, and the outputs are the centerline trajectories. And so basically this is how this looks inside the finite element model. So now what they want to do is they want to do a control loop where you have a control policy that could be nonlinear. So it's a model predictive control, basically, MPC, that goes into your robot. Your robot is fully nonlinear. You have an output measurement model, which are the 40 points along the center line. And then you need a state estimator. So from the output, you need to re-estimate the state, and the state goes back into control. That's a classic control loop. This state estimation has to happen in real time for this robot. So that's where we want to do a reduced order model. This is a simple state estimator. I mean, controls people love linear problems. So this is why our operator inference method here will look at learning a linear state estimation model so that they can use it in control. And again, they wrote it as a first order. I mean, this is a time stepping. We kind of did like a second order system here to get this discrete time system. They ran it, and one of the things they found here, so they compared, they got a state estimation, they did a control policy, and then they kind of like actuated this robot. One of the things that they found in simulation is a way to control this. So they control individual chambers separately, and they found that the top segment has to be actuated the heaviest, and the tail segment has to be actuated the least. And here's the actuation signals that would come out if you use the norm of the controls, if you use certain different methods to build your state estimator. I'll talk about this later. So what they did, they compared three methods, dynamical mode, linear methods, because they need this to be linear and fast. Dynamic mode decomposition with control, eigensystem realization or Kalman identification, ERA, and structure preserving operator inference. What they did here on the right, sorry, this is a bit grainy. They compared eigensystem realization in open loop and closed loop operation, DMDC in open loop and closed loop, and operator inference in open loop and closed loop. And we look at a certain trajectory here, so the zeroth output here, and we look at how this output evolves over time. And we see that with second order operator inference, we're doing a very good job of tracking this, both in open and closed loop. So the state estimator is pretty good. And resulting controllers. So this is a good model for what they want to do. And in the second, this is in training and this is in testing. So as we go, even in the predictive scenario, sorry, again, it's kind of grainy. The purple curves, which are Lagrangian operator inference, really overlap with the ground truth quite well. This is as accurate as a roboticist would hope for this to be. And then we do testing for, we randomize they randomize the initial conditions and run it for different cases. So they get a root mean squared error basically, and they test in open and closed loop. And we see that Lagrangian operator inference does best in all of these test scenarios. Now you ask yourself, and this is where I take 5 more minutes to say, okay, so everything was good here. Our takeaways are that this seems to be reasonable for this application that they have. It works well in open and in closed loop. But there were a few data sets where the nonlinearity is just so strong that we need to do something about it, that even a linear state estimator might not be good enough. And so in other problems, aside from the robotics applications, for nonlinear waves, I showed you Hamiltonian at the beginning. We kind of always had to make this assumption that we know something about the PDE Hamiltonian. And that's not fully satisfactory, but that's what the best we could do at the time. So now you could ask yourself, so then we started working with people in structural engineering. They wanted to use this method, but they basically enhanced this method to use some more machine learning in it to avoid having to know things, because they work with experimental data where they don't quite know what the model is. So now we augment everything I've shown you before. I'm looking again at the forced Euler-Lagrange equations, but I'm allowing myself basically more nonlinearity. I allow myself to have, again, a nonlinear component, just like I had before in the Lagrangian setting. I'm also allowing myself to have this nonlinear component in there. I have a more general viscous damping than I allow myself here as well. So there could be other damping terms that are not just linear. And ultimately, I would come up with this Lagrangian system here that now has highlighted in blue things that we in collaboration with our structural engineering colleagues have added to this framework. So we don't have to rely on linearity. Again, linearity seemed to be fine for the robots. It's probably, it wasn't fine for the nonlinear vibrational tests that the structural engineers were looking at. Okay, so our optimization problem now becomes a little bit harder. It's not just optimizing over linear constrained operators anymore, so not optimizing over M, C, and K, but we also have to optimize over these functions now. So we would like to find out which functions do we need there. We split this up into 2 things. The first part is we just learn the linear parts. So we learn the linear part of this problem, C and K, so C and K. And in the second step, we learn the nonlinear perturbations of that problem, okay? And that's where we use some structure preserving machine learning to learn the dissipation function and the reduced potential energy functions. So now you have to parameterize the problem, of course. I mean, you can't learn over functions. You have to parameterize the function. So we choose a neural network representation, which uses, actually, it's these multi-layer perceptrons that David felt like they were a good way to use, but we want to augment them with polynomials too. Oftentimes you have polynomial nonlinearity. So if that's the case, you're doing a polynomial regression here, just of higher order. Not with operator inference, we learn linear. With this, we would learn up to, I think, 4th order polynomials. And if the nonlinearity is still different from that, then these MLPs kick in. Okay, and you can make this 8th order if you wanted to, but so we parameterize this problem. Obviously, now there's a lot of free parameters we have to learn, these alphas, the lambdas, the gammas. And for the reduced kinetic energy, we do the same thing. We allow ourselves, so here we only use polynomials. And that allows us to get a perturbation of the identity mass matrix out, which was previously something that we didn't have in the framework, by computing the Hessian of this energy. Okay. And now I'll spare you the cost function, but the cost function is basically this function over here. We try to minimize that error over everything, such that we have structure preserving constraints. So we always want the energies to be positive. We can never get variables that give us negative energies. You know, we want to do the same with like the kinetic and the potential energy. So those are the constraints that make this a structure preserving method. So in 2 minutes, I'll show you the last application, which we're quite excited about. So this is the half-break Royce beam, which is you can access again the data from this website here. The method was described in this paper. So basically what happens, you have 2 cameras, high-speed cameras. You have a beam that's jointed in the middle. So you have a couple of bolts that go in. In jointing structure, there's obviously contact. And friction and a lot of nonlinearity happen in the middle. So you cannot really understand. So writing down the governing equations of that joint is really hard. And modeling it with linear is also not working. So that's why we're looking at nonlinear methods. So these cameras give you digital image correlation measurements because there's like sensors that are on top or kind of like reflectors, so you can measure things right of this beam, and you get these this nice data set. But at the same time, it's a beam, so it's vibrating in 2nd order, so we can incorporate that. So on the left side, we're plotting now. This is an unusual plot, I would say, in our community. We look at the position versus frequencies, so certain frequencies of excitation, frequencies of the beam versus position, and the displacement amplitude. This is the experimental data. So this is the DIC measurements that we have. And on the right side, so now we take these measurements, we learn a Lagrangian operator inference model that is linear plus a structure preserving machine learning model. So a fully nonlinear Lagrangian model. We predict things with order 3, and we get what's on the right-hand side. Our structural engineering colleagues are very happy about this. We can look at other things like displacement, amplitude, position, and damping ratio. So what's the damping ratio as a function of position as you go up and down this half beam, and we kind of recover that pretty well too. Those are the same scalings on the left and on the right. Okay, that brings me to the end of my talk before I go to the next slide. So these are what I wanted to show you as some experimental results as well. So before I conclude, let me use the time to advertise. Advertising a conference that is very much in the theme of this seminar series, which we have in San Diego at on basically our campus. So it's the Model Reduction and Surrogate Modeling Conference. It's running in San Diego in September 9th to 13th. If you have nowhere better to be at that time, you should be here. It's a great time to be in San Diego. It's a great community. It's a single track conference, you know, usually around 150 to 200 people. Great way to mingle with senior faculty, junior faculty, meet peers, everything. Covers all aspects of model reduction, surrogate modeling, applications, UQ design. You can sign up by submitting a talk, no paper or anything, just a talk, 1-page abstract at this website. Application, and this closes March 1st. For graduate students that are on here, we'll also make available pretty soon some funding that we have so that you can apply for, so to get travel supplements to come to San Diego, so we can make this affordable for all affordable and accessible to all graduate students and early career postdocs. So now I want to review. I've shown you that embedding geometric and mechanical structure in the case of Hamiltonian, Lagrangians, or other gradient structures is really great, and it's a way that people with physical and engineering knowledge can embed what they bring to the table. They give us interpretable models that are long-term stable. They're accurate. And I haven't shown you this much, but in some of the papers, we look at the need for training data, and we need less data to train structure preserving things. The methods I developed, I want to highlight, they don't just work on a 1D test problem. We've worked on them on experimental problems from structural mechanics, experimental problems from soft robotics, and so they work pretty well there, which I'm very happy about. Looking ahead, I think neural networks have great expressive nature. They're not as nicely interpretable as we found as symbolic expressions, and so looking at more symbolic forms of these nonlinearities would be something we want to do. And extrapolation in parameter space is always a big question. So I'll take any questions here, and thank you again for the invitation. And the last thing I wanted to point out is that actually one of the invited keynote speakers is the host of the seminar, Yung So Choi.
Thank you,
Okay.
Boris. Yeah, I strongly recommend all of you to join this conference.
Yeah.
Yeah. Cannot emphasize more. Thank you, Boris. Yeah, and also thank you so much for the wonderful talk. That was really nice. Let's have a Q&A session. Yeah, there is a questions in the chat and by Jack. He asked, would this approach work for a high dimensional problem like a molecules? Doing a full dynamical calculations of even a small molecule is very difficult, or even an atom. A full calculation of electronic structure has 6 n dimensions. So any comment about that molecular?
Yeah, obviously, I mean, in some of these, I mean, first of all, you have to identify if, you have a Hamiltonian or a gradient structure or Lagrangian structure. That's something that typically you would know from the physics. Dimensionality wise, I mean, you have to run the simulation first and see if there's low dimensionality in it, which is what we do with using the singular value decomposition. So if you see a reasonable decay of singular values, then you have hope of doing this low dimensional. I would expect that's the case. But I can't speak because I don't know the application very well.
Right.
It really is application dependent how the physics allow you to approximate this.
Right. You have a one of the problem was solving the nonlinear Schrödinger equations, and
Yeah.
and the first principle molecular dynamics people, they are actually simplified and then come up with a DFT, like the density functional theory, and they solve it, and I guess there is a connection between the Schrödinger equations and molecular dynamics. Maybe there is something here it can propagate to.
Could be, yeah.
Yeah.
And it's certainly an area that needs it in terms of dimensionality reduction, yeah.
Yeah. And their structure preserving is really important. So so definitely there is a connection. So maybe I can ask questions. So you talked about the polynomial augmentations at the end, close to the end, and you tried up to the fourth order. Well, I guess you probably studied lower order, tried the lower order or higher order, and then add the neural net. Was that right?
Yeah, basically. I mean, I think we stopped. Obviously, the higher order you make it, the more parameters you get to learn. So there's a trade-off between going to 10th order and learning thousands of parameters or going to keeping it at fourth order. There was some Pareto curve, I presume that we had seen there that we felt p is equal to 4 is a good thing. But I don't have the data at the moment. I would have to ask for this specific data set. I would have to ask David who did that work why it should be equal to 4.
Good. So you have plotted the Pareto front end based on that plot.
I believe so. Yeah.
Okay. Sounds good. All right. Any other questions from audience? Our group is working on energy conserving intrusive use the auto model for Lagrangian problems right now.
Oh, nice. Okay.
Yeah, but yours are non-intrusive one, the one you presented today, like using the inference operator, right?
Yeah, still, I mean, once you do intrusive, maybe things can be done non-intrusively too.
Cool. Yeah, that we should talk.
Yeah,
Definitely.
definitely.
Because I mean, intrusive I mean, we are specifically looking at the Lagrangian hydrodynamics, and there
Okay. Yeah.
and there we get like super energy conserving. So if you look at the energy constraints,
10 to the minus 16.
yeah, like almost like 0, like 10 to the
Yep.
negative 12, 10 to the negative 13.
Yep.
and
That's excellent. And that's why these methods are so, I mean, so great, I think.
yeah. So we definitely need to talk.
Yeah. I mean, intrusive is kind of the, I don't know, it really is, if you can, and you guys invest the time to go into your, I don't know, what is it, Largos or whatever the code you have.
Yes.
Yeah, you go into it and you do it. I mean, I would stick with that if you can. There's but
Yeah, the thing
in
is,
some
it's
applications where you can't, like
exactly,
those measurements we had, or the soft robotic stuff, the software is so hard to access that we've tried for half a year to get it intrusively, and then we just gave up and said no.
Yeah, that's what happened with the intrusive method usually.
Yeah.
You
So
demonstrate really well in one applications, and in order to apply that to other applications, you have to put pretty much same amount of effort implementing it.
yeah, I mean, if you have your own code, it's perfect because you understand it. But if you
Right,
work with
right.
other people's code, and what
Yeah.
we ran into, that every time there was a software update, something didn't work anymore. So if you have your own code and you have control over that, I think that's the way to go then.
Yeah. Totally agree. Can you make some comment about the one of the examples you compare the DMDC and your the quadratic model using the operator inference, and the speed up is comparable pretty much.
Yeah,
Taken
I mean,
first.
in that case, they were, this was this was in the robot stuff. Let me see here. They're all linear methods. So, I mean, there's no difference. I mean, it's just a different way that we learn. We have constraints in the way we learn the linear method, and we solve a second order system. DMD and ERA are first order, like system ID methods. But once you have the solution here, I mean, they're all linear systems, so they're all pretty fast. There's no difference. The only difference, I mean, when we compare things here, we compare actually the best model that we can get from any one of them. So it could be that, DMD needs like 25 modes and we need only 12 modes, but we compare a 25 against a 12 mode system because we say that's kind of like, this is the best model, this is the best model. So let's let the two best models compete. But nevertheless, we still find that understanding that there is second order structure and symmetries is really what gets you that.
Awesome. Okay. Is there any questions from audience? Don't be shy.
They can email me too. Perfectly happy with that.
Yeah.
Okay.
Well, if not, let's thank our speaker today, Boris. Thank you so much. It was wonderful talk and very nice.
Thank
And
you.
definitely, let's keep in touch.
Yeah. Thanks for the invitations, and thanks for everyone taking time this morning.
Awesome.
Thank you.
All right.
Bye, Jungso.
Bye, Boris.